again, you're using this learning catalytics business. I think most of you are probably experienced with this, but for those of you who took the course a couple years ago, it's new, and so we're doing instead of clickers, so we're giving it a try. So you got to make sure the way you do it is you log into Mastering Physics from Portal, right? And then once you get into Mastering Physics, you log into this, and I think there's something that says Join Session. And then what happens is when I come to a clicker question, I'll send you the clicker question through your device. So we'll try this out together and see how it goes. Okay, and so hopefully you found the pre-class video, and so we're going to start off with the chapter 20, I think, in the Wolfson text, and so we're starting off talking about electric charge. And so just right away we like to kind of just talk about, the smallest amount of charge we have is the proton and the electron charge. And this is 1.6 times 10 to the negative 19 coulombs. So it's sort of an unfortunate unit, right? You got to be real careful with your calculator and stuff. But one idea here is that this charge is really small, right? So a couple of questions. So again, thank you so much. Your questions last night were great. And so what I'll do is I'll sort of pepper them in the lecture depending on where they might be more applicable. And so when I read the textbook, I found that 1 coulomb is equivalent to about this many elementary charges. What is an elementary charge? Well, again, this is the elementary charge, so it's a proton or electron. And so there'll be questions the book will ask that sort of deal with that. They'll say, suppose this much coulomb is in your pocket. How many electrons is that? And basically, you just take the number of coulombs and divide by the charge of 1 electron. All right, and then, so this happens, so the book, I think, talks about some particles like quarks and stuff, just to kind of go for an aside. And so you get questions like this, like, do we need to know that for our tests and exams? So, I'll do this too, the book will do this, we'll sort of talk about stuff. I mean, we try to make it really clear what's open for tests and exams. We have our old tests posted, we'll do lots of homework, we'll do lots of examples. I mean, basically, if we don't spend much time on it in class, then I would not worry about it, okay? And then here, this is a really interesting question. If nothing makes a charge negative or positive, since we only use these terms to describe why a charge behaves a certain way, what is stopping us from calling electrons protons or vice versa? This is actually a pretty deep question, right? And there really isn't anything stopping us. Right? It's just convention. We'll find out in a few weeks that actually the way we picked it is kind of a pain, right? Because the thing that's mostly moving is electron, and electrons are negative, right? When they first sort of were understanding charge, they didn't really know what was happening, and they just sort of made it up, okay? But in some ways, it would actually make our homework sets a lot easier if we switched these, okay? But of course, due to history, we don't. But that's a really great question. Nothing is stopping us. It's just, I think you can blame Ben Franklin if you want to. He's the one that sort of did some of the first pioneering things with charge. So the key that we're going to use here is this idea right here. So this is one of the fundamental things with our electric force. Like charges repel, so if I have 2 negatives, they're going to repel each other, and opposite charges attract. And the force will be along the line connecting the 2 charges. Okay, that's basically all we need to know right there to start understanding this stuff, at least on a conceptual level. Okay, this sort of idea right here. That, along with this concept, which is superposition, which is really important, and this is something that happens in physics a lot, this idea. So what do we do if there's more than 1 charge that can apply a force to our point charge? And of course, the book is going to love to do that, have more than 1 charge. What do? Well, we use this idea of superposition. And basically what this says is that all we have to do is find each force individually and add them up. All right? And so it's sort of the easiest way you can imagine this working, and luckily it works. Okay? And that's great. So in the example at the end of the pre-class video, when considering the force caused by B or C, is it always okay to consider them as forces acting separately on A, or do they also act on each other? Now this is a great question. So they definitely are going to act on each other, right? But usually with this kind of stuff, you're asked about, what is the force on charge A? Or, there'll be some charge that you're kind of focusing on, and when you're focusing on that charge, you can always add them up separately. Okay, so we'll talk a lot about this, we'll do some examples, but that's what this law of superposition is. Okay, you can always add these things up separately. So here's another sort of deep question. Regarding the superposition principle, how do we actually know that multiple forces in charge distributions simply add vectorially in nature? If so, what are some specific evidences of this? That's actually a great question. How do we know? Well, there's a lot of things in physics, like F equals ma, for instance. Okay, we've seen that seems to work. And basically, the way it works, or how we know it works, is that it does. Okay, you can't really prove it. It's just that when you do experiments, F equals ma seems to work. It's the same thing here. The superposition principle works. Okay, if I have two charges and I use the principle to figure out the force, that's the force we measure when we do experiments. Okay, and so there's not sort of some fundamental thing. It's just basically that's what works. Okay. All right. So here we go. Our first learning catalytics question. You guys who've done this before, let me know if I'm doing this correct. So I believe I just sent this to you guys, I hope. Okay, and so here we have a conceptual question. This is like actually an old test question, I think. So we have 3 charged spheres arranged as below. What direction will the electric force on charge A point? And we just say assume the charges have the same magnitude. Okay, so which one of these options here, A, B, C, D, or E, is correct? And so we're trying to find the direction of the force on A. Okay, so talk to your neighbors and see what you think. I think the response I saw was most people agreed with this answer here, which is what I had, which is great. So let's just real quick talk about that, because there were a few people who were off, but I think, again, most of us got that. So the idea here is we just use this sort of picture we were just talking about. Okay, so we look at the two forces individually. So I'll start by looking at the force acting from this charge over here. Okay, that's going to be a force of repulsion. So it's going to sort of go this way, something kind of like that. The other direction of the force will be attractive, something kind of like that. All right, and so if you look at these two forces, the one thing you realize is that the length of these arrows should be the same because all these charges have the same magnitude. Okay, so this arrow should be exactly the same because the distance of separation is the same. And so when you look at this is something that's going to happen a lot this semester, is we'll have a vector situation where it's sort of up and down, and you just sort of reason to yourself, well, if I break this into its components, they look like this. And what's going to happen is the up and down component here will exactly cancel. This one will double up, and so the overall force will be that way. Okay? Questions, anybody? Okay? Okay, great. So that concept is pretty solid, so that's good. So let's move on now to this one. So lots of questions on this one. And again, this is from the pre-class quiz. And I would say this is a hard one. Okay, so like I said, I think the differences between 131 and 132 as far as how we run the course, the pre-class questions is probably, I think, the biggest one. And so there'll definitely be questions like this that are tricky. And so let's work through this and kind of try to unpack it a little bit. This is kind of a classic question that they do with this sort of thing. And so the way I look at this is I try to break this into regions. And so let's look, sort of draw ourselves a little picture. So here's our little setup. Here's a positive charge, and here's our negative charge. What I like to do is I like to draw it a little bit bigger so that we know that it's a bigger charge, all right? Because that negative is 1.5 and that positive is just 1. And then what I do is I put what they call a little test charge sort of in the 3 different areas that we're interested in. Okay, and I look at that little test charge there and I think, what force is that test charge going to feel? Okay, and so I'll label these 2 charges, charge 1 and charge 2. And so in this region here, from charge 1, this guy's going to feel a force that way. All right? And then from charge 2, we don't really know how these things relate to each other, but we can say that there'll be a force of attraction from charge 2. So the 2 forces that my test charge feels in that region are in opposite directions. Now if we put a test charge in between, how does that work? Well, so for my force F1, there'll be a force of repulsion. there'll be a force of attraction from that one, F2. Those two forces are in the same direction, okay? And then finally, if I go into this third region of interest and write my charge there, I'll see that there's an attractive force from F2 that way, and a repulsive force from F1 that way. So again, I'm not thinking really right now about how big these arrows are. I'm just sort of thinking about their direction. Okay, and so the idea here is we want to know is where on the x-axis can you put a third charge that would experience no net force. And so if you put it here, there's no way these two forces can cancel. So this cannot be correct. Okay, so just by drawing this picture, I know that in between here cannot be correct. All right, and now I look over here, and I look over here, and I sort of think, well, those are in different directions, so they could possibly work, right? And so we want to think a little bit more about that. And so here's some questions from students. So I'm confused by exactly what a test charge is. Is it the charge creating the electric field? So the test charge is just, so this charge that I put in to like a region just to kind of test the region out a little bit. You know, in general, it's pretty small, but it's just sort of a word we use in physics. You know, I could have called it anything, but I call these little guys here test charges. From the question in the pre-class quiz, if a charge were to be added in between, this would affect the initial electric force between Q1 and Q2, correct? Totally. So this would affect the charge of these guys, or the force that these guys are feeling, okay? But the thing is, these guys are fixed. And so these guys aren't allowed to move, okay? So the charge will definitely, you know, if I put this in here, it'll affect, you know, a force on one of these two guys, but we don't really care because these are fixed. They're not allowed to move. And so we really only care about the force acting on our test charge, okay? And so here is another question, you know, if there are forces between particles, would they move? Well, again, here, we're assuming these two guys are fixed, okay? And we'll do that in most of these problems, you know, unless we stay otherwise, we'll sort of assume the charges are fixed. And usually we'll try to be clear about it too, but just in case. And here's the big question. I think it would matter what the charge of the particle is, because if it was positive, it would have to be put somewhere different than if it was a negative, although I'm not really sure. Okay, so some great questions there. So let's go ahead and try our next question. And so this is actually from last night. So last night we did this one here, and it went okay, but let's see how we do today. So make sure, again, you can talk to your neighbors and see what you think about this one here. Where could you put a charge where it would cancel out and be zero? So that's great. And again, just to reiterate, you know, whether you're right or not on these clicker questions makes no difference, right? It's just that you answer. Okay, and so the answer is to the left of Q1, all right? And so let's go back to our picture here and think about this. Okay, so here's our picture we drew, all right? Now, so what we were saying when we drew this picture is that, well, the only place that could possibly cancel was here or here. And so the question is, which one is correct? And so pretty much everybody voted over here. Why is that? Well, the short answer is that basically you've got to find a place, okay, where the charge can be closer to the smaller charge, right? Because the two things that affect the force to charge effects are the size, you know, of the charge and how far away you are, all right? And so when you're in this region over here, okay, over here, this test charge is closer to the smaller charge and further from the bigger charge, and so those two effects can cancel, right? And so you basically get to a point where you're far enough from this one where the two forces are going to cancel out. Over here, that's not possible. Over here, you're always going to be closer to the bigger one, and so you're always going to feel the force of the bigger one as a stronger force. And what I try to use, like the example I use is, imagine these are two people talking, and this person's like talking really, really loud, and this person's whispering. If you're over here, you're never going to be able to get to a point where you're close enough where you hear them the same. You're always going to hear the louder person more. If you're over here, there's some sort of magical spot where you can go to where you'll hear the whisper person at the same volume as you would the loud person, okay? And then sort of the final thing that I think threw some people was, well, doesn't the charge matter? Well, let's go through and sort of do our little picture again. Okay, so let's do our little picture, and this time I'll use the test charge as a negative charge. Well, here, the negative charge, so what this does is it changes the sort of order of these, so F1 is now that way, and F2 is now that way, but the actual nature of these doesn't change. They're both in opposite directions. Okay, and the whole size of the charge thing works exactly the same. And so in both cases, it's still going to be this side is the side where it's going to cancel out, right? And if I put the negative charge over here, the same sort of thing, I'm going to feel repulsive from F2 and attractive from F1. And the negative in here is the same sort of thing, just now it's opposite. So F1 is that way, and F2 is that way. So this is how I sort of think about these kind of problems. A lot of people asked, how would I actually calculate the answer? We'll talk about that next time. Okay, so for right now, we just sort of got the idea of sort of how to figure out where it is. We'll actually calculate the number next time. Okay, so a lot of questions on this one. Anybody got any other questions or, yeah?
Is there a mathematical way to prove that no matter how much I put the positive charge on the right-hand side, it would never able to reach equilibrium state? Or
sure, yeah, and we'll talk more about the mathematical side of this next time. But yeah, you could definitely, basically you can write the equations out and there'll be no way to solve them, right? Well, we're not going to worry about from a mathematical proofs, yeah, but you could set it up for this one, sure. Other questions on this one here? Okay, great. So like I said, a lot of questions on that, and so I think that's kind of a hard one, but you guys are really good. Awesome. Okay, so just a little bit more sort of talking about the course. So this is the course schedule. If you go to Portal and hit course schedule, you get to this link, and this has most everything you need. So let's just sort of talk about a few of the things. So first of all, this is lecture 2. Right here is the reading in the book that we're covering. Here is the slides that I'm going through, and then once I'm done, I'll put the slides with notes up later. Over here is the link to the pre-lecture video for this week. Again, ideally, this is sort of covering the same material from here. Over here in this row, we sort of tell you what's due, so you know if there's homeworks or anything like that due. And then over here are problems from the textbook. All right, so these problems are similar problems to what we're doing today, and so if you want to get some practice, you can do those. They're purely for practice. They're never to be turned in, okay? It's just for practice. A couple other things on Portal. Now this is actually the Portal page from last year, but you have a similar thing. If you go to course materials, there's a thing in there for test prep. And so there's test 1 materials. And so for test 1, right now we have 2 actual old tests from the last 2 versions of Physics 132 that I wrote. And then here, I sort of put a collection of basically every other test question I've ever written for this kind of material. Okay, so the hope is that there's so much in here that you have plenty of practice. So here's just a copy of what your pre-class quiz looks like. I just wanted to sort of discuss 2 things. So first of all, it's really hard to get Mastering Physics to mark on only effort. And so what we do is we make the questions here for practice, and there's one question here which is really the marking one, right? And it basically says, did you do the pre-class quiz? Always answer yes to that. So if you answer no, we can fix it, but it's just kind of tricky. But the idea is you just answer yes and you get the points for all the work you just did. The other thing, and this is just for me, so this question here is not required. Okay, and what happens is a lot of people are afraid not to answer a question, okay, and so they just put no or something. And that's great, and some of them are really polite, but it really gives me a lot of baggage to go through, right? And so it's easier for me if you don't have a question to just skip it. I guarantee you, okay, you'll never get marks taken off by skipping it, okay? But it's just easier, if you have a question, that's great. I want to hear your question or a comment, but if you don't, just go ahead and skip that. So are they marked for accuracy? No. They're marked for effort, okay? And so someone here, looks like so someone said, going into the pre-class quiz, I was unsure of what to expect, and as a consequence, I went in blind and ill-equipped to answer the questions. Well, first of all, I do tell you the reading, and there's a video, so hopefully that'll help you a little bit, right? But kind of the whole idea is that I want to know how much of this you know. So if you don't know it, then just sort of do the best you can. You're not measured on accuracy. right? The idea here is, number one, I think it's good to think about the problem before you come into class. Like if we had just done that problem before in class, you would have had like 5 minutes to think about it, but now you've had a couple hours to kind of think about it maybe. And also, I can take your results and sort of get an idea of where people are getting confused and stuff like that. So it's super helpful for me. All right. The other thing you'll find on Mastering Physics is basically a link to all of those extra problems I assigned. Again, you don't have to do it. This is all for practice. It says not for marks. Okay, but you can find them all on here. And the nice thing about that is you can, so this is like one of the questions from chapter 20 that we could work on right now, is so you can do this on your laptop, but even better, if you are doing this and you're having trouble, hit the give up a button and it gives you the answer. Okay, so I can put like even questions in there and you can still find the answer to even questions. Again, you don't have to do these, it's just practice, okay, but you have the ability to go in and find the answers and do all these practice questions. Okay, and so someone asked, do we have to do all the questions? Well, no. I mean, you do as much practice as you want, but the only thing you have to do is the Mastering Physics assignments, right, and the pre-class quizzes and stuff. Everything else is sort of, if you feel like you need more practice, do it. So my office hours, so these are the office hours I have right now. So what I've been doing the last couple of years, and it works pretty good, is I head over to this room here, which is one of our practical rooms. And I'll basically sort of answer questions from people for like a few minutes. If you have a quick question, do that. And then I head over there, and it's a big room, and so if we get like 20 people in there, we can kind of do a larger office hour or something. So it's just sort of, and so basically after class, I'll go straight to there. And then right now I have this office hour, and we'll sort of see how it goes. We can maybe add more later or something. You can always make an appointment. And if you just sort of drop by, I'm almost always available to talk. So that's good too. Just real quick too, I think most people here have probably done this, but if you have bought an older version of Mastering Physics, email us and we can get you into this one more than likely. Okay, so just send an email to the 132 email. And then here's just some questions you guys had. Are the pre-class lectures similar in information as the in-class lecture? Well, they're pretty similar, but again, they're different. I use your results from some of the pre-class stuff to change the in-class stuff, right? But they'll definitely be similar. So here's someone wants tips about learning Physics 132. So I think what this person is saying is most of this stuff is new. So I think some of you might find that a lot of the material in 131 you had before, and then maybe this stuff in 132 you haven't seen so well. Okay, so just that's something to think about. Can the due date for the pre-class quizzes be right before the lecture? So this is a real common question. 8 a.m. is kind of a bummer time, right? Basically, the problem is I need time to take your answers and kind of tweak my lecture, right? Like I used to have these due at midnight, and then people were like, hey, can we move it past midnight? I'm like, sure, let's do 8 a.m. And now it's like, so 8 a.m. is not great, but it gives night owls a chance to do it, I guess. But the idea is I need time to sort of put the lecture together, right? So, yeah, question?
Ago when you said when you were in your office and you said T, is that Tuesday or Thursday?
That was Tuesday. It needs to be posted on Portal, yeah. Do you have to remember the formula and constants? No. So the test will have the same test sheet. Okay, you can write your same sort of test sheet as you did for 131. So the test will run, we'll go more over this when we get closer to the tests, but it'll be pretty similar. And you can actually look at the old tests. The old tests have their cover page, and so you can read and see. I think it's pretty similar to what they did last year. There's maybe a few differences, but nothing too major. So here's someone who didn't like writing essay questions, so they're not optimal in my opinion. A multiple choice is not only much less time consuming, but it was also effective for learning. So it's definitely more time consuming to write an essay question, but that's really where I get my information, right? So I can look at the multiple choice and get some idea, but the essay questions I can really sort of see what you guys are thinking and if maybe, things I can do to help you more. Okay, so I know it's definitely probably more work, but for me, it's much more effective for me. And I also think, what happens a lot in science is like when I was in your guys' shoes, our test was just all number problems. right? Everything, the answer was all numbers. There was no questions about concepts or anything. And so you get the idea that really the only thing we care about is doing these problems. And the problems are important, but we also really want to understand the concepts. And that's where I think it can be really good to have to put some of this stuff into words. That's not easy to do, but I think it's a good process sometimes. Okay, so in regards to the pre-class quiz question, I can only think about it logically and conceptually. I'm having a hard time expressing it using the equations. So that's the tricky part, right, is sort of balancing this sort of being able to do the sort of the math and also the concepts. So we're going to try really hard to connect those, but yeah, that's not easy, right? That's definitely, I think, hard. All right, so the last thing then, again, with the PCQ responses, I need a couple sentences. I need some kind of an explanation. Here's an example from last night of things that probably aren't super helpful. Okay, so someone who said other two cases are wrong, right? Someone said the force and the two charges would cancel out. So I guessed balance, right? And so it's just what will happen. So right now you get a point for this, but what will happen is I'll give you guys a few weeks to work it out, but I'll start deducting points for answers that aren't, complete. All right? So keep that in mind. This is my favorite one because of science, right? You can't really argue with that, right? But again, not super dig that. Okay, so we're going to do a little demo here just to kind of show you some cool stuff you can do. So this is similar to what you're going to do in lab coming up here this next week. And basically we're going to use a lot of sort of charging things. And so, so here I've got just a pop can. And I've got a simple glass rod. This is like the same glass rod you'll have in class. And what I'm going to do is I'm going to rub it here with this animal fur. And what that does is it charges, or it basically transfers charge from the fur to the glass. Okay? Now this is just a regular pop can. It hasn't been adjusted at all. And what I can do is put the pop can on the ground and then take this thing, okay, and it attracts the pop can. All right, and I can do this either way that I want to. And I can even stop it and go and make it go the other way, yeah. So that's pretty cool. So you can do that to your friends, kind of like magic, right? So again, we'll do this in practicals next week. And I wanted just to kind of explain real quick what's happening there. So we'll talk about this a lot as we go on, but this is what's called the idea of polarization. Okay, so that pop can, the pop can is a bunch of positive and negative charges that are usually together, right? It's like, and so they cancel out. But what happens, and I'll just maybe make this clear, this is pop. So let's say pop. So when I bring the rod over here, let's just say that the rod was positively charged, okay? What that does is, in the pop can, okay, the electrons are free to move. It's a metal. And so what happens is when I bring that positive charge, it attracts negative charges from the can. And so what happens is a bunch of negative charges will kind of get together here, and that'll leave a bunch of positive charges over here. And so we say that this thing is polarized. Okay, so it's still technically neutral, all right? There should be, maybe I didn't do it, but there should be as many negatives as there are positive, but it's polarized, okay? A bunch of the positives are over there, and so what happens is the pop can will be attracted by my positive charge, okay? This is an important idea because next week you're going to do this yourself with some balloons, and the problem is once you have something charged, okay, like this rod, okay, it's basically going to attract just about anything because of this idea of polarization. Okay, so you got to be careful when you're charging things up because basically it's going to be attracted to everything and it can kind of be confusing. And so here this pop can is neutral, but it was still being attracted by my rod. Okay, so let's carry on. So now we'll get into some a little bit more mathematical stuff here. This is Coulomb's law. This is the mathematical version of sort of what we've been dealing with, all right? And so it tells you the force on a point charge from another point charge, like say on Q1 from Q2, and R is the distance between the two charges. And K is just this constant here. Okay, again, you never have to memorize this. Someone asked about this little sort of hyphen here. This just means it's Newton times meters squared over Coulomb squared. Now again, what makes this tricky is that it's a vector. Okay? Now, the way I prefer to do these is to think about this equation as an absolute value. Okay, so we'll go through and do an example. There's an example in my videos too, but we'll do basically an example, and we use this and treat it as an absolute value, and then we draw in our vector arrows sort of the same way we did in the first part of the course. We use our head to think about it. And so for me, that's easier, and I think it leads to less mistakes. The book does it a little bit more of a mathematical way. If that's how you prefer to do it, that's great. You can do it any way you want. I'm just going to sort of show you what I think is the easiest way to do it. Here's a student question from last night. So since Coulomb's law applies to point charges and to charges that can be concentrated equivalently in points located at the center, would that imply that the size of a charged particle is much, much smaller than their distance of separation? Yeah, basically that would have to be true. In order for Coulomb's law to work, okay, that R must be really, really much bigger. Sorry, that's not a good way to put it. It should be very much bigger than the size of the thing you're talking about. Now, electrons and protons are super, 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 super tiny, and so it's never going to be a problem for us. But when you get to bigger things, okay, it can be less of a, you could have sort of problems with your accuracy there, but that's a good thing to be thinking about. Okay, and so here's the question that we're going to do today. So there's 3 charges. This is, again, I think, an old test question that I asked years ago. And so, sometimes the book is really mean, and instead of giving you numbers, it just gives you letters. This is an example of one of those. And so there's 3 charges. This one is a charge Q. This one is a charge 3 times Q. This one's a charge 5 times Q. And then we tell you that this is a distance D, and that's a distance D. Okay, and what we want you to find in this test question is the total force acting on this charge here. Okay, and so the first thing that I do is I draw a little picture of the direction of those forces. Okay, so the force so there's 2 forces acting on this one from the 3Q, and I call that F3Q, that points straight up. Okay, so we assume that if these are all the same Q, they're all positive charges, so they're repulsive. And then the 5Q is going to apply a force F5Q going this way here. Okay, so that's sort of the first thing that I would do when looking at this, is sort of draw my picture and sort of write out my vectors the way that I think they should go. Then the next thing I would do is use this new equation, Coulomb's law, to start calculating some stuff. Okay, so again, the absolute value of the force acting on our charge from the 3Q would look like this. So I take my Coulomb's law, and so I'd say K, and then I put in the 2 charges. And so one of the charges is 3Q, one of them is Q, and then it's all divided by what we call D squared. So it kind of makes life a little bit easier here, that just the distance here is just that D. So it's this here, and then what I'm going to do is just kind of try to simplify that a little bit to be 3K Q squared over D squared. All right? And now the way I like to then express this is as a vector with x, y coordinates. Again, you can do it any way you want, but that's just the way I like to do it. It's basically the same thing as the book using I and J kind of stuff. And so in this case here, my particular vector is all in the y direction. So I'd have 0 in the x direction, and then see if I can fit it in here, 3K Q squared over D squared here, and of course this would be positive, okay, because we're sort of just going to assume we have our usual x, y coordinate system like this, x and y, and so this force is pointing in the positive y direction. Okay? All right, so now let's have you guys do this for the other charge. So I'm going to send you another question here. All right, so which one of these choices is the correct force magnitude from the 5Q charge on the Q? So think about this with your neighbors and see what you come up with, and we'll discuss in a little bit. There's some math involved here, so it's a little trickier than your sort of typical one, but it looks like most people have answered. So let's maybe give ourselves, like 30 more seconds to sort of put a response in here. I think I agree with the majority here, so that's pretty good. So we did pretty good on this one, I think, I would say. And so it is choice B. And so writing this out, the sort of the similar fashion we just did, F on 5Q, so this would be our K constant, 5Q is the one charge, Q is the other, and I'm going to leave this as R. And of course R is this distance right here. So this is the one that's a little bit tricky here. R squared is going to equal, if you just do a Pythagorean theorem, d squared plus d squared. And so R squared would be 2d squared, and so I just basically plug that in over there. And so my force 5Q is going to be K Q squared over d squared 5/2 out front. Same thing we got here. Okay, so again, so the first thing we did is we drew the direction of our arrows. The next thing we did is we go through and find our two magnitudes. And so the final thing is we're going to sort of add up those two vectors. So my force of the 3Q, right, we've written out as being 0 and then 3K Q squared over D squared. And so now what I want to do is write out the other one, this guy here. And so how do we do that? Well, the easiest way to do that is to think about this way. And so basically this force, F5 of Q, we just wrote it out as being 5/2 K Q squared over D squared. And by looking at this geometry here, I can see that this angle is 45 degrees. And so this will be the tricky part. Okay, but this little triangle here is basically going to have the same dimensions as this triangle does over here. And so this angle here is going to be the same as that angle there. And since it's both side D, okay, that's going to come out for us to be 45 degrees. And so that sort of makes our life easier. And so what we can see then is like sort of this side here, the x component of this would be the magnitude, 5/2 K Q squared over D squared, and this would be times cosine of 45. And if you work this out with your calculator, you get 1.76 K Q squared over D squared. And so when I figure this out then, I get 1.76 K Q squared over D squared, and since this of course is 45 degrees, they work out to be exactly the same on both sides, like that. And then just the last thing I like to do is just check the signage of those. And of course those are both going to be positive sign because they're pointing, again, if we sort of think about our XY axis is the traditional XY axis, it looks something kind of like that there. So this guy is pointing positive and positive. And so your last step to sort of get this is just say F total. So if I add these two up, 1.76 plus 0 is just this over here. And then 1.76 plus 3 is 4.76. All right. Now, the last thing, and a lot of people asked this last night, is how do I leave my answers? Well, unfortunately, like the book and me and tests will sort of ask different ways. We'll try to be clear. You know, if we're not clear, this is totally fine. That's the vector. You know, leave it like that. But here we were sort of clear. It says, what's the total force, magnitude, and direction acting on that Q? So it wants the magnitude and direction, not the components. All right. And so you got to go back to sort of thinking about this vectorially. And so here I just sort of put my F total again, 1.76 K Q squared over D squared. 4.76 K Q squared over D squared. And so what I usually do is draw myself a little triangle at this point. And so what I want to do is sort of figure out what my hypotenuse is and what my angle is. And if I don't define an angle, you can just use any angle you want to. And I know that my x component is 1.76 K Q squared over D squared. And this is 4.76 K Q squared over D squared, like that. And so what I do is I just go through. So first of all, hypotenuse is going to be these two sides squared. So 1.76 K Q squared over D squared squared plus 4.76 K Q squared over D squared squared and the square root of that. And when I went through and did this, I got something like about 5.07 K Q squared over d squared. Okay, obviously this is a little bit easier if they give you numbers and it's not in letters, but I thought it'd be good to do one in letters just so we've sort of done it as hard as we could. And then the last thing is to find that angle. You got to use some sort of trig identity or something. And so here I'll just say tangent of theta, right? We know that that equals opposite over adjacent, so SOHCAHTOA, right? And so we get 4.76 kq squared over d squared, 1.76 kq squared over d squared. What's nice is the whole kq squared over d squared thing cancels, and I get 4.76 over 1.76. When I take the inverse tangent, the theta I get is 69.7 degrees. And so if this is a long answer then, you could just sort of say, well, the magnitude is the 5.07 kq squared over d squared, and the magnitude of the theta is 69.7. So as you can see, this is going to draw on our knowledge of vectors, which I think typically we haven't been using a lot lately. And so you might sort of have to go back to 131 or math and just kind of remember some of this stuff. But I think usually this stuff comes back pretty quick. Any questions on this one here? So again, I'll post these notes so you can always go through this yourself. And there's lots and lots of practice questions as well, right, of this kind of topic. So before we still have some time left, everybody. So I thought we'd do just like, let's see. So just real quick, this is one of these just sort of student questions. Okay, so for the answer to the final question that was shown in the video, how should we be writing the full answer? Well, again, it'll sort of depend on how we ask it. Is there a faster method to find the net force than what we did? Well, if you can find it, that's great, do it. This is how I do them, so I don't think so. Can you explain the significance of the r hat unit vector? So we got asked this a lot. The book does this in terms of the r hat unit vector. If you like that, or if you learned that in high school, please do that. That's fine. We'll never ask you any questions about that specifically. It's just a different way to sort of think about this than how we did it. Okay, but it's up to you, but you don't have to worry about it. Okay, so an example question done in the video with point charges A, B, and C. Is there a force between the charges B and C? So we talked about this. There's definitely a force between all the charges, but we're generally going to be focusing on just one of them. Okay, so we'll go ahead and call time there. So I'll be outside here, and then I'll head over for office hours. Thanks, guys. We'll see you next time.